Welcome back, Contemporary Math. We are in Chapter 7a. So we are going to start talking about, this section is all about probabilities. And so we will start talking about probabilities in the section. Then in Chapter 5, we'll start talking about basics of statistics. And so if we want to think about probabilities, we're probably going to do a lot of coin flipping, a lot of rolling die, and a lot of selecting cards from playing cards, and doing things that are to simulate sort of random picking, right? So the first thing we want to do is flip 2 coins, or if you're really cheap, I guess you can flip 1 coin twice and consider them separate trials. But there are basically 4 different ways it's going to end up if we flip 2 coins. If we flip 2 coins, they could both come up heads. One could come up. First coin could come up tails, and the second could come up heads, or vice versa. So we are distinguishing which coin is which. We're distinguishing this one from this one, or if you're doing 1 coin, you're distinguishing the 2 trials, right? And so we come up with this thing, and we're probably just going to use the letters from now on. I'm not going to write out the words every single time. But H, H, T, H, H, T, 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 this might look fairly familiar. If we just replace the H with an F, I think we get a really similar pattern to like what was in the street tables. But this is like you have 2 options, and you have 2 propositions, right? You're going to have 4 options. And so we talked a little bit about that previously with the multiplication principle. We'll talk a little bit more about that later in the section. And so they throw out 2 words at you, so they come up with an outcome or an event. So an outcome, there are 4 different outcomes here. It's the most basic possible result of an observation or experiment. So one outcome is heads, heads. Another one would be tails, heads. Heads, tails would be another one, and then tails, tails would be the last. So event would be like saying, what is the event of getting 1 head? So there, you might notice there are 2 different ways that we could possibly get a single head. And so both of those outcomes would fall into the event of getting 1 head. Okay, so we want now, instead of toss 2 coins, we're going to toss 3, and we want to think of every possible outcome. What are all the possible events if you're only considering heads? Okay, so sometimes if you want to do every possible outcome, sometimes they do this sort of branching diagram. So on the first round, they either get tails or heads. On the second, if we get tails on the first, it's here. Tails or heads here. Third, we're counting all the possible outcomes. If we're counting all the possible outcomes, you might notice there are 8 possible outcomes. So this is hopefully like, you notice the sort of pattern might look familiar to like what our truth tables look like. If we had 2 propositions, we would have 4 options. If we had 3 propositions, we would have 8 options. There are 2 possible outcomes for each proposition. There's 2 possible outcomes for each coin. Things might look sort of analogous. So I want to sort of follow this thing along. If I want to do just the letters, I can follow this thing along. T, T, T is one of my possible outcomes. So if I want to list all possible outcomes, T, T, T is one of them. T, T, H would be the next one. So I can follow this along, going the utmost branch, going the utmost, and then going to the next one, going the utmost. Well, I already did all those. So now I've gone to the next one, going as utmost as I can. THT, I think is the next thing. Would be the next thing, HTT, HH, HHT, and I believe I'm on HHH. So these are all the 8 possible outcomes. If we want to know the events, where I'm getting my outcome. My events is how many heads I can get. So the least amount of heads I can get, if I'm doing 3 different coins, I can get 0 heads. I can get 1 head. I can get 2 heads, and I can get up to 3 heads. There's pluralized heads. So basically I can get 0, 1, 2, or 3. Okay. So a little bit about the notation and how we express probability. And I would hold on to this. If I'm being honest, we're going to come back to this and talk about this thing a little bit more later. I would definitely hold on to that thing a little bit. But a little bit about the notation about how we express probability. So if we want to say the probability of heads, so this is tossing just 1 coin now. Consider tossing a fair coin, means fair meaning it is equally likely to land on heads or tails. It's a 50-50 toss, right? It's a 50-50 percentage. So the probability of landing out of heads is the number of times it's going to land out of heads over the total possible outcomes. So there are 2 possible outcomes. Half the time it's going to land on heads, or 0.5 would be the probability. Probability of tails is going to look exactly the same. It's going to be a 0.5 probability, and think about all the possible outcomes. If it's going to land on either heads or tails, that's everything. Whew. Whoa. Whoa, whoa, whoa. Did a copy paste job. 2 over 2 is not 0.5. Sorry about that. This should definitely be number 1. If we add up every possible outcome, it should be a probability of 1. So talking about probability, the probability of an event, if I say there is a 0 probability of something happening, that means that event is impossible. It's not going to happen. If I say there is a probability of 1 of that thing happening, that means something is guaranteed to happen, right? If we flip a coin, it's going to land on either heads or tails. If it lands on the side, I don't know what to tell you. We're not considering that. You call him a cheater? I don't know. Pull up the revolver if you do at birth. I think every Texan's got one. You call him a cheater. You tell him to be on your way. Okay, so probability of an event expressed as P of an event is always between 0 and 1. 0 meaning it's never going to happen, so the lower it goes, the closer to 0, the less likely it is to happen. 1 is guaranteed to happen, so the closer it gets to 1, the better off we are. But it is going to be a fractional amount. If we say 50%, right, it's going to be like 0.5. There's a 50% chance of heads happening. Didn't miss anything in this thing, so let's see. Note on rounding, so they give a little note on rounding in the book. They say to 3 significant figures. So that means basically after all the zeros, you want to grab 3 numbers or 3 numbers before a bunch of zeros, right? You want at least 3 good numbers in there that aren't zeros. Is kind of what they're hinting at. And I think that's pretty much what I've been saying. Like around 3 or 4, you usually be pretty safe in this class. Theoretical probabilities. So there are basically 3 basic methods to finding probabilities that they want to talk about in this book. The first one is theoretical, the second is relative frequency, and the third is subjective. if I'm being honest, the first two are really the things that are probably relevant in this class. The third one's a little bit silly, but they throw it in there, so we'll talk about it. And if I'm being honest, I don't really think the theoretical method and the relative frequency method are a lot different. There's just one little sort of assumption we make with like theoretical method and relative frequency is we're observing things. So theoretical method for equally likely outcomes. So we're assuming that things are fair, right? If we're tossing a coin, it's going to be fair. It's going to be random what side it lands on. If we're rolling a die, it's going to be fair. It's going to be random what side it lands on. So count the total number of possible outcomes. Among all the outcomes, count the number of ways the event of interest A can occur. And the probability that an event can happen is the number of ways it can occur over the total possible outcomes. And so this is what they're giving you in the book. This is the way you find probability of an event. So a little bit of an example to add context to it. So apply the theoretical method to find the probability of exactly one head when you flip 3 coins. So right off the bat, I hope you can figure out when I flip 3 coins, the total number of possible outcomes when I flip 3 coins. Back to that first page, there are 8 total possible outcomes. Now we want to count all the outcomes that have exactly one head. So that would be 1, 2, 3, and that is it. So there are 3 of them here. So we have 1, 2, 3. This one has no heads. This one has 2, 2, and 3. So those are the only 3 that have one head. So there are 3 out of 8. Or we can say the probability of getting one head is going to be 3 out of 8. You can write that as a fraction 0.375. Okay, so the probability of getting a 4 when you roll a 6-sided die. There are 6 possible outcomes. Right? If you get a 6-sided die, if you want to do 4, there are 6 total possible outcomes. The 4 is only one of those possible outcomes. If you want to do the probability of getting 4, it's going to be, if we went around, I think it's like 0.16 repeating, something like that, 0.167. Okay. And so we're doing coin flips, we're doing dice. What is the probability of drawing a heart? What is the probability of drawing a 5? And so if you're not familiar with playing cards, you probably didn't go to public school or have to play card games while other people are taking tests. Remember, that's all we did during toss or tax, whatever the heck they want to call it now. And so it was that in the UIL contest. It was always playing cards. So probability of getting a heart. So there are 52 cards in a deck. So maybe a few numbers just they're out there. There are 52 cards total. If we look at the deck, it's divided into 4 suits. It's divided into clubs, diamonds, hearts, and spades in that order. It goes ace. Sometimes ace is 1, sometimes ace is 10. But typically start off with it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then there are 3 face cards. what is the probability of drawing a heart of 5? So we're looking at this thing. If we're looking at 52 divided into 4, there are 13 cards in one suit. Might be another way to think about this. There are 4 of each card. If we talk about an 8. So what about a heart? What is the probability of drawing a heart? So there are a few ways we could write this. So we could think about this as there are 13 hearts out of a total of 52 cards total. You might know for drawing from a deck, and we divide top and bottom, it's a 1 in 4 chance. It's one of the suits out of the 4 suits is another way to think about it. Or I guess we could write this down as the 0.25, right, is what 1/4 is. Okay. If we're looking at this next one, what's the probability of drawing a 5? So if I'm looking at drawing a 5, there are 1, 2, 3. There are 4 5s out of 52 cards. So the probability of drawing a 5 would be 4 out of 52, or 1 out of 13, which gives me somewhere about 0.0769. Okay. If we're looking at this one, you select a person at random from a large group attending a conference. What is the probability the person has a birthday in August? Assume there's 365 days in a year, and that births are equally likely to occur on any day of the year. And in the book, they go on this bit of a tangent to say births aren't really evenly distributed, and you probably really shouldn't do this. Did I meant to change this, and I didn't in the problem. Okay. I don't want to do August. Let's say April. That's a bit different. I meant to do April. Okay. So I always really hated that rhyme whenever they taught you how to memorize what months had what days. But if you look at your knuckles, there's a little knuckle trick you can do if you start labeling, let's see if I can get a knuckle on here. January would be on a peak, February would be in a valley, March would be in a peak. So if you start labeling January, February, March, April is in a valley. So that's one of the 30-day months. So if we want to know April, if there's 365 days total, April would account for 30 of those, or 30 out of 365. Which, if you plug it into your calculator, you're going to get something like 8.0822. Okay. Okay, so way back when we did logic and stuff, we talked briefly about this multiplication principle. But this is sort of like, I give an example, like I have 2 roads going from the first city to the second city. Then maybe I have 3 roads going from this city to this city. And I ask you, how many routes are there? And if you want to follow this thing, we can take the first road. And then we can take the first road, and we have 3 options after we take the first road. The other thing is that we can take the second road, and then we have 3 more options. So we have 2 by 3 is the way that we're doing it. If we want to know our options, and we have 2 options here, and we have 3 options here, the total number of options, if we combine the two, would be 6. So similarly, when we were doing what? 2 coins. We had 2 options by 2 options. We had 4 total options for 2 coins. If we want to do 3 coins, there's 2 options. It could be either heads or tails. And so we have a total of 8 options or 8 outcomes like we had mapped out here, right? We listed them all out. You might notice each time it's going to get multiplied by 2 every time we go. If we're talking about a coin flip with 2 options, right? If we do a coin flip and a dice flip roll, it might be a little different. We might have to multiply by 6s, right? So with this said, this is theoretical probability. We are assuming things like the dice is equally probable to land on either side. The coin is equally likely to land on either side, right? So that is making sort of assumptions about the way that these things are going to behave. And these are the way that they would behave sort of ideally, right? And in reality, when we talk about reality, things don't behave ideally, right? So that is kind of the main difference between our theoretical and our relative frequency probability. So when we talk about the theoretical, we're making this assumption everything's equally likely. We're making all these ideal assumptions. Here, we're just conducting the experiment and we're seeing what it does. So it is the same approach. We're still doing the number of times they occurred over the total number of observations. So instead of outcomes, I guess we're doing observations. And we're just looking at how many times it occurred out of the total number of trials that we're doing. So here we're actually conducting the trial. In the previous ones, we're doing it all sort of theoretically. But finding the probability is the same basic concept. It's the same approach. It's the number of times it occurs out of the total number. Previously, we were talking about all possible outcomes, and we're making all these assumptions like it is random, it's going to be ideal, right? Here, we just do it and see what it looks like. So if we have geological records and they indicate a river has crested above a particular high flood level 5 times in the past 3,000 years, using the relative frequency method, what is the probability that the river will crest this flood level next year? So we can use these relative frequencies to determine things like the probability of it being flooded, right? The probability of something happening, right? Based on what has happened in the past. So geological records 5 times in the past 3,000 years. So out of a total of 3,000 years, 5 of those years, this river, is it river? Yeah, the river has crested, right? It has flooded. What we're doing is the flood over the total number of years. How we're finding this probability. So the probability it will flood is probably the thing I should say. P flood is going to be the number of years it would the flood over the total number of years, or the 5 out of the 3,000. This is 0.0067, I think, is what I'm getting. So that is less than a 1% chance. It is very unlikely to happen, right? But even unlikely things do happen, right? Okay. Okay, ooh, move this down. Example 6, this is where it's going. Suppose you're rolling a 6-sided die, and you're rolling it 100 times, and you observe the following. It lands on an even 53 times, and it lands on an odd 47 times. We want to compare the relative to the theoretical. So I want to think first about maybe like the theoretical. So if I think about the probability of it being even, well, I have 1, 2, 3, 4, 5, 6. So how many of those are even? 2, 4, and 6 are even. I get 3 even out of a total of 6. So you might figure out like the probability of it being even is going to be a half or 0.5. It is going to be even half the time, and it's going to be odd the other half. That's sort of 50-50. It's either going to be even or odd probability. So this is the theoretical probability. And I want to compare that to my relative frequency. So the relative frequency they give me for even is 53 out of 100 versus 47 out of 100 for odd. So I'm getting 0.53 and 0.47. And this is sort of like I'm talking about, right? Ideally, right, we want a 50-50 sort of thing. This is going to happen half the time. This is going to happen half the time. But relative frequency, right, might be a little bit different from what ideally happens. It might be different from your theoretical probability. But would we still say that this is a fair die, or would we say it's unfair? So 0.53 is really close to 0.50. 0.47 is really close. It's really close. And in reality, things don't match up exact, right? And so I would say that there's probably not enough reason to suspect that the die is unfair. It's pretty close. There's not enough info, right? We would need more info if we wanted to dismiss this as being unfair. It's probably fair. But it probably is, based on what's happening. Okay, so the last thing, and it's kind of silly, but they talk about it in the book. It's subjective probability, and it's just like an estimate that you make. It's just based on what your life experience or your intuition. And so basically, these are the 3 different ways we have to finding probability. We have a theoretical probability where we make assumptions about things being equally likely. We look at all the possible outcomes and we say, how many times does that event occur out of all the total possible number of outcomes? Relative frequency, we actually conduct the experiment. We look at the number of times the event occurs out of the total number of trials that we conducted. And then the last thing is subjective probability is an estimate based on experience or intuition. Okay. So I think just getting an example of subjective probability and you can see what it'd be like. Identify a method that resulted in the following statements. I'm certain you'll be happy with this car. So I hope right away. If you read the sentence, this has absolutely no numbers in it. So is that theoretical probability or relative frequency? No, that is neither one of those. So this one is what we're saying subjective. Some kind of opinionated statement based off of what you sort of know. It's not even really involving any math, right? So that's their subjective statement. I'm sure you'll get married next year, right? Something like that. I don't know. I'm sure you'll be happy with this car. Something along those lines. Based on housing data, the chance that someone will move to a new residence during the coming year is 1 in 8. So based on housing data, or the probability of rolling a 7 with a 12-sided die is 1 in 12. So we want to think about which one of these is theoretical and which one of them is relative. So based on housing data. So this is saying that they're basing it off an experiment. So that should hopefully be kind of a giveaway. But here they're talking about a relative frequency. They're observing something happening, reporting back how many times the event happens out of the total number of occurrences, right? They're looking at all the residents, and then they're looking at that one of them moves out of 8 of them, right? When they reduce this fraction, it's going to be 1 in 8. It's, the next thing is probability of rolling a 7 with a 12-sided die is 1 in 12. This is the thing where they assume everything is equally likely. There are 12 possible outcomes. 7 is one of them. This is a theoretical probability. Okay, and the next thing, and I believe it's the last thing on here, is we want to talk about the probability of an event not occurring. Ooh, no. There's one more after the event not occurring, I believe. No, I'm thinking about the next section. So we do the probability of an event not occurring, and then we do a few things about odds. There's a little bit about vocabulary about stating about odds. The way they talk about odds is a little bit odd, so we got to discuss that. So if the probability of an event A is the P of A, or P of A, yeah, probability of A, we write, I almost want to say probability of A anytime I see P of A. We write the probability that event A does not occur as P of not A. So either A occurs or A does not occur. This goes back to that logic thing. It is either A or not A, right? Because an event either does or does not occur, the sum of the probabilities. If we think about everything, every possible outcome, they should sum to 1. Something should happen, right? And if we think about everything, every possible outcome should sum to 1. If we want to get not A from this, and we want to solve for P not A, the way we would do that is by subtracting P of A. So 1 minus P of A should give you P of not A. And so maybe an example. When flipping 3 coins, what is the probability that you will not get exactly 1 head and 2 tails? So the probability of getting same thing as an event of getting 1 head. This is going to be 3 out of those 8. If we go back to this first page and count them, this is 1 head, 2 tails, 1 head, 2 tails, 1 head, 2 tails. There are 3 different ways. If we think about this, this should be another way to write one. You can think of it as 8 over 8 if you wanted to, so that we can find maybe a common denominator. But if we do 1 minus 3/8, what we're going to get out of that thing is 5/8. Okay. And if we go back to this picture, hopefully that should make sense. We have 8 total possible outcomes. If 3 of them are 1 head and 2 tails, there are 5 of them that are not 1 head and 2 tails. And so that's what they're saying with this property. If we do 1 minus, an event, it gives us the probability of that event not occurring. And 5/8, I think this gives me, I didn't give the decimal, but 0.625. I should probably give the decimal because that is usually how we express probabilities is between 0 and 1 as a decimal. Although sometimes it is easier to express it as a fraction. So we want to talk about making a probability distribution. So if you want to make a probability distribution, you got to know how to find your relative frequency or your probabilities. But we want to make a probability distribution for this set, and the event is in the heads. So if we want to do 0 heads, there is one way we're getting 0 heads. That's if we get all tails. So there is one way out of 8 we're going to get 0 heads. There are 3 ways out of 8 we can get 1 head. We talked about that. If we talk about 2 heads are better than 1, we get 3 different ways to do that. And we get 1 way to do 3 heads. That's all heads. And this is probably getting back at, it might be easier to keep them as a fraction, because if I look along these fractions, 1 plus 3 plus 3 plus 1 gives me 8/8. I guess you could add those decimals if you really wanted to. You probably got a calculator, so it's probably not too hard. They should sum up to 1 if we're summing up all the possible events or outcomes. Okay. So this is how I make a probability distribution table. We do the event, we do the probability. The probability should sum to 1. If we want to do the same thing, we can do a probability distribution with a bar graph or a bar chart. And here we group them into categories or events of 0 heads, 1 head, 2 head, 3 heads. And if you look along here, I get what 0.125 is where this should be, somewhere around 0.125. This should be somewhere around 0.375. It's not quite to 4. Those are the numbers we got. If we sum up all these numbers, they should sum up to 1. So typically your probability doesn't go beyond 1, right? When you do these charts. So imagine a person is shuffling 3 cards, an honest 3-card monte that only exists in math class. They have a 3 of diamonds, a jack of hearts, and the ace of spades. They shuffle and let you pick on 2 separate occasions. Assuming you didn't follow the card and your guess was equally probable, fill in the following probability distribution table, considering the event of getting an ace of spades. So we could get, we're picking twice, so we could get none. We could get no ace of spade on both pick. We could get one of them, get it on one, but not the other. We could get it on both of them. So if we think about this, branch chart might be a good way. We have a 3 and a jack. Is that what we have? On our first draw, we have an ace 3 or a jack. On our second draw coming off of that, we have an ace 3 or a jack. But it's okay. 3. So it looks like I should have 3, 6, 9 different possible outcomes in this thing. Ace, 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 jack, ace, jack. Okay. How many ways are there to get 0 ace of spades? have a total of 9 total possible outcomes. How many of those involve 0? This involves 1, 1. 1, 2, 3, 4. I believe there are 4 out of 9 possible ways to get 0 ace of spades. How many ways are there to get 1? It looks like 1, 2, 3, 4 different ways you could get this. 4 out of 9 here. I maybe should make my graph a little bit bigger. Okay, and then the other thing, how can I get 2 ace of spades? There is one way to get 2 ace of spades. And so if I sum them all up, they should give me 9 out of 9, or should give me 1. So if I want to make a probability distribution table, the first thing to do is to list all my possible outcomes. After I list all my possible outcomes, I get my theoretical probability. I fill it into my probability table. And we should probably check to make sure the sum is 1. Okay, so now we went ahead maybe a little bit of a different direction, do something a little bit more complicated. But I kind of have all your outcomes here. So if we're thinking about the sum when rolling 2 dice, I can get a 1 and a 1. My sum is going to be 2. So in these boxes is the sum of the dice. So if you think about rolling the first die and then rolling the second die and summing those 2 numbers, the lowest that's going to go is if you have 1 plus 1 on your die. It's going to give you 2. So the highest that thing is going to go is up to 12. So you might notice there are a few ways to get like 3. There's a few ways to get 4. So if we're looking at 4, 3 and 1 is going to give us 4. 2 and 2 is going to give us 4. 1 and 3, right? We can do 3 and 1 or 1 and 3 either way. If we add the same 2 numbers, it should give us the same number. So this is all my possible outcomes. If we look and count them up, there are 6 by 6 total possible outcomes this thing could give me. Some of those are the same event, but there are a total of 36 different possible outcomes. And we're considering getting a 3 and a 1 kind of different from getting like a 1 and a 3, right? They will give me the same event, but they will be separate outcomes. So we're thinking about this thing, there are 36 different ways these 2 dice could land. Okay. If I sum them up and I want just the event of the sum, you might notice 2 is happening 1 time out of a total possible of 36. 3 is going to happen twice out of 36. 4 is going to happen 3 times out of 36. 5 is going to happen 4. 6 is going to happen 5. So I'm counting like down the diagonal there. They're all the same number. 7 should be the most, and there are 6 7s. You might notice some of these fractions are reducible. If you're doing a probability distribution table, this might actually be the better numbers to throw in there, not reduced. And I'll show you why in just a second. But if we go to 8, there are 5 of those 8s in there. 4 9s up in here. 2 10s up in here. 2 11s. And exactly 1 8 to get this. And a little bit why I did not sum these up or simplify these is because now we can sum them up. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. Was it 6 plus 6 plus 6 is another way you can do it. This is 6, 1, 2, 3, 4, 5, 6 times. That'll give us 36.
it is easier to sum up your probabilities if they all have the same denominator. Okay, stating the odds. So this is like just basically a vocabulary sort of thing that they're testing on. So the odds for an event A are given by odds for event A is P of A compared to P of not A. The odds against an event A are given by odds against event A are P of not A to P of A. And in gambling, typically when they say odds on, they're talking about the odds against something happening. So I think I've got 2 more examples. We're going to bet on some horse races in a second. Okay. So what are the odds for getting exactly 1 head when tossing 3 coins together? What are the odds against it? The odds for 1 head. Exactly 1 head. We have kind of done this already, but it is from the definition as the probability of getting 1 head. The probability of not. The probability of getting ahead is 3 out of the 8. The probability of not getting ahead is 5 out of 8. Okay, so you might notice this is the same denominator, but if we wanted to simplify this or get rid of this denominator, one way we can do that is we multiply top and bottom by 8. But if we do that, basically we're going to get 3 over 5. 3/8 over 5/8 is 3/5. And so sometimes we might say something like 3 to 5 is the odds. You might see something like 3 to 5 are the odds. They are the odds for getting exactly 1 head. So the odds against is the same thing flipped, right? P of not 1 head over P of 1 head. And so now instead of 3/8 over 5/8, we're doing 5/8 over 3/8. You might notice that looks very similar, except we're flipping it. It's the reciprocal. It is 5/3 or 5/2/3. Okay, so now we're doing the last one is a horse race. Okay, that's the real horse's name. So at a horse race, the odds on Hoof Hearted are given as 10 to 3. If you bet $15 on Hoof Hearted wins, how much will you gain? If I'm being honest, before this class, I would have had no idea what they're asking. It is crazy sort of vocabulary that they use when they do these bets. But what this is meaning is that for each $3 you bet, you will make $10. These are odds against Hoof Hearted is what it is. This is if they win, you will win $10. That's assuming they win, right? If you don't win, then you're just losing your money. So if I bet $15, what is that like? That's kind of like I'm doing $3 bet 5 times, right? And if I'm doing this 5 times, one way I can think about that is that I'm going to end up winning $50. And there's a little thing that like a lot of people forget, but you're gonna win $50, and you also paid $15 for your ticket that you're gonna get back. So $65 should be the takeaway from the window. When you go turn in that stub, when you go turn in that stub, it should be a $65 takeaway. And maybe just a little bit more about this, just maybe get what they're getting at. So we're gonna do odds against our horse, Hoof-Hearted, our not him. I would P of him. This is 23. And so what we did is we ended up placing $15 on Hoof-Hearted. When the odds against them are 10-3, if we place it on the Hoof-Hearted, right? We want to find out 10 over 3 is 1 over 15. This is that thing that looks like 3x equals like 10 times 150. Then I get $50 in winnings. I gotta add back my $15 for my ticket. So my $65 is what my ticket should be when I go turn it in. Or I should get back $65. There's an odd thing that, like, I think the $50 is usually people do enough studying in this class and they get the $50. It's that little $15 going back and adding it, right? You got to remember to do that thing. It's one of those little things that you get so caught up in the hard part in the vocabulary, sometimes you forget to go back and add that thing. So we want to have $50 winnings, and if we already paid $15 and we want to end up $50 up, we got to add these two things together is what's happening. All right, so that is the last problem. I will see y'all soon. Take care.